Hi, I'm Dan Smits, and for my final project today, I'll be presenting wireless security protocols for WEP WPA, WPA2, and WPA3. In this presentation, I'll provide an overview of how each protocol works, their evolution, security weaknesses, and the differences between them. This presentation will focus specifically on the authentication and encryption algorithms used to secure Wi-Fi. As with all information systems and the technologies that facilitate communication within them, the goal is to protect the confidentiality, integrity, and availability of the data while in transit and at rest. Wireless communications are particularly vulnerable as there's no physical mechanisms to safeguard data wirelessly. Security protocols are used to secure these communications to find the use of cryptography facilitating communication. Wi-Fi security is specifically managed by the Wi-Fi Alliance to ensure compatibility and interoperability between various manufacturers. In order for a manufacturer to bear the Wi-Fi logo on their product, they must implement security protocols as defined by the Wi-Fi Alliance. As Wi-Fi Alliance develops security protocols to protect Wi-Fi, they are incorporated into the IEEE 802.11 standard. Over time, four primary standards have been developed to secure Wi-Fi communications. Those are wired equivalency, privacy, or WEP, which was part of the original 802.11 standard, Wi-Fi Protected Access, or WPA, which is in its third iteration, as the Wi-Fi Alliance continues to update the standard to counter vulnerabilities and utilize the latest security protocols. The first standard developed to protect Wi-Fi was WEP, which was introduced in 1997, and with the first commercially available Wi-Fi products, the standard provided minimal security as there were significant vulnerabilities quickly discovered by hackers that allowed them to determine the authentication key very quickly. Modern computers can exploit WEP encryption with scripted tools and extract the authentication key in seconds. The exploits have evolved to the point that no hosts have to be connected to an access point using WEP, as the attacker can use the authentication process to extract the authentication key with the access point. As we'll see on the next slide, the vulnerabilities for the standard are part of the authentication process, and weak encryption was used. The standard only uses a 10 or 26 digit hexadecimal key with a 24-bit initialization vector, making it vulnerable to brute force attacks with modern processors and GPUs. WEP utilized either a pre-shared key to restrict access to only authenticated clients, or open authentication, which used RC4 encryption to secure data in transit for all users without authentication. The initialization vector in WEP's 24-bit random value that is used to seed the RC4 algorithm. RC4 is a stream cipher. This means that for each bit of plaintext, it produces one bit of keystream and XORs the two. To generate the ciphertext, the keystream is simply a stream of random numbers generated from the RC4 algorithm. In the most basic operation of the stream cipher, the algorithm is seeded with a key, such that the same key will always produce the same stream of random numbers. Since both the client and server know the key, they can produce the same key stream. This allows the client to XOR the plaintext with the keystream to produce the ciphertext, and the server to XOR the ciphertext with the keystream to produce the plaintext again. The problem with this is that the key is only a few tens of bits long, but the plaintext may be gigabits. After a large number of bits have been produced by RC4, the random numbers become predictable and may even loop back round to the start. This is obviously undesirable because no plaintext attack would be able to compute the keystream and use it to decrypt new messages. In order to solve this problem, an initialization vector was introduced to complement the seed. The IV is a random 24-bit value that is changed periodically in an attempt to prevent reuse of the keystream. Unfortunately, 24 bits is quite small, and the IV often generated wasn't in an unpredictable way, allowing attackers to guess future IVs and use them to deduce the key. Further attacks involved actively injecting packets into the network, tricking the access point into dishing lots of new IVs, which allowed attackers to crack WEP in minutes or seconds. In order to address the significant vulnerabilities in WEP, the Wi-Fi Alliance developed Wi-Fi Protected Access, or WPA, in 2003. While WPA in its first iteration still used the RC4 stream cipher, it implemented a temporal key integrity protocol, TKIP, to address the issues with the static key used for encryption. While most client devices could be upgraded through firmware, the uses of CRC checks for data integrity and TKIP required many access points released prior to 2003 to be upgraded to implement the standard. WPA also allowed enterprise clients to utilize a separate server for authentication using the extensible authentication protocol. Small home office users now had the option to continue using pre-shared keys, but it was no longer limited to hexadecimal and could be encrypted with a 256-bit key and larger initialization vector of 48 bits to increase the difficulty in predicting reuse of IVs. WPA2 expanded on the initial implementation to further upgrade encryption. Originally, WPA was meant to be backward compatible with WEP. In WPA2, in lieu of any kind of backwards compatibility, AES replaced RC4 cipher with TKIP for authentication. For backwards compatibility with clients, TKIP remained a fallback when the cipher block chaining message authentication code protocol, or CCMP, cannot be used. The mechanism to fall back to TKIP has remained a vulnerability to WPA2, as the four-way authentication handshake also could be used in WPA, can be easily captured, and then brute force attacks can be conducted to reveal weak passwords. The availability of low-cost cloud computing infrastructure such as AWS combined with GPU hacking has made this standard somewhat vulnerable to determined hackers. In 2017, a vulnerability discovered in which an attacker could perform a key reinstallation attack known as crack to exploit the reinstallation of wireless encryption keys. Because the crack exploit exists at the encryption stage, both pre-share keys and extensible authentication protocol are vulnerable. In the next slide, we will discuss the authentication process used in WPA and WPA2 to illustrate how it is exploited. In this example, with message 1, the access point sends a message with a no-ons random number to the device to generate a pairwise transit key. The client device knows the access point's MAC because it's connected to it. It has the pairwise master key, the S no-ons, and its own MAC address. Once it receives the A no-ons from the access point, it has all the inputs to create the pairwise transit key. In message 2, once the device has created its pairwise transit key, it sends out the S no-ons, which is needed by the access point to generate the pairwise transit key as well. The device sends the message to the access point in message 2 with a message integrity check to make sure when the access point can verify whether this message is corrupted or modified. Once the S no-ons is received by the access point, it can generate a pairwise transit key as well for unicast traffic encryption. Message 3 is sent from the access point to the client device containing the group temporal key. The access point creates the group temporal key without the involvement of the client from the group master key. In message 4, fourth and last, will be sent from the client to the access point just to confirm that the keys have been installed. Once this is done, the control port is unlocked. Once the four-way handshake is completed successfully, the virtual control port, which blocks all the traffic, will be opened, and now encrypted traffic can flow. Now all unicast traffic will be encrypted with the pairwise transit key, and all multicast traffic will be encrypted with the group temporal key, which is created in the four-way handshake process. Because the client and the host both know the pairwise master key or pre-shared key, they exchange the A no-ons and S no-ons to derive the pairwise transit key to encrypt traffic. By capturing all components of the handshake, the attacker can derive the pairwise transit key and use it to generate a mashing hash of the pairwise master key. More recently, in 2018, WPA3 has become the successor to WPA2. New devices released since 2020 are required to support the standard, and some legacy devices have been updated through firmware. The standard mandates the use of protected management frames, which are designed to prevent eavesdropping and packet forging. The use of 128-bit encryption is standardized, and while AES continues to be utilized, it now supports up to 256-bit keys. WPA3 addresses the crack vulnerability in WPA2 by changing the authentication method to simultaneous authentication of equals, which is a version of the Internet Engineering Task Force Dragonfly handshake, which we will review on the next slides. SAE eliminates the reuse of encryption keys. SAE also limits users to active on-site authentication attempts and flags anyone exceeding a certain number of password attempts. SAE mandates a new encryption passphrase for each connection using a technique called forward secrecy, which aims to prevent cracked passcodes from being used to encrypt data previously captured. The standard also adds the ability to easily add IoT devices to the network with QR codes. Unfortunately, many security researchers believe WPA3 was a missed opportunity due to a new Dragonblood exploit, which works by downgrading the device to WPA2 so that previous exploits can be accomplished. The degradability of WPA3 was a feature by design to ensure backwards compatibility. There are two phases of SAE authentication, the commit and the confirm phase. First, we'll go over the commit. The client and the access point goes into phases of commit and then confirm. Once we have a commitment, the client and access point can then go into the confirm states each time there's a session key to be generated. The method uses forward secrecy, where an intruder could crack a single key but not all the other keys. In the commit phase, the client generates two random values, A and A, and then computes a scalar value of A plus A. The value that the access point will pass is the PE or password equivalent, such as hash value of the password that the client and access point know, raised to the power of negative A. As the values will get large, the operations are done with a mod Q, and where Q is a large prime number. The client does the same, and then they exchange values. In the end, they will have the same shared commit key, which is PE to the power of AB. They will only have the same shared value if they both use the same password. This password is thus used to validate the client and access point, and they will only have the same shared commit value if they both have the same password. An intruder cannot determine either the original password or the final shared value. In the confirm phase, we then use the long-term key to generate a unique session key. An attacker cannot determine the password used or the long-term master key. The cracking of one session key will also not reveal the rest of the keys which have been used due to forward secrecy. This is not the case for WPA2. In general, typically the advice provided for these standards is to use the latest one that your devices in your network can support. Any security is better than no security. However, the exploitability of WEP would provide little to no barrier to entry for an even novice hacker equipped with Metasploit modules and scripts. WPA3 finally corrects the four-way handshake that allowed keys to be reversed in WPA and WPA2. However, the backwards compatibility function WPA3 to downgrade to WPA2 makes it equally vulnerable. Some manufacturers will likely implement a force option for WPA3 to prevent downgrading, which would be the best option. For larger institutions, the extensible authentication protocol with radius server is typically recommended to control access on a per-user basis and prevent all users from sharing a single pre-shared key, as is done by consumers. Key exchanges with hash passwords will continue to be the Achilles heel of Wi-Fi until zero-knowledge proof authentication protocols are implemented as the standard. Consumer access points are improving in the default security settings, and many newer devices will by default be set up with the latest standards. ISPs are also taking a more proactive role in protecting small and home office networks by providing access points and routers as part of a service package, which are often remotely managed and monitored. There is a privacy trade-off with service providers implementing this level of access, but the benefit to most end users likely outweighs this concern to prevent breaches of their networks. The driving factor for many of the newer versions of wireless security standards have been the vulnerabilities identified by security researchers, which evolved into scripted exploits. As computing resources become cheaper and more powerful, particularly with cloud infrastructure, it is likely standards will have to evolve faster to counter these threats. Consumers' networking equipment may have a shorter shelf service life, based on the need for faster upgraded standards, which is probably why many ISPs have implemented a rental model to facilitate this transparent to the end user. Cellular broadband technologies such as 5G may eventually replace conventional home wireless networks with virtual networks co-managed at the service provider level.